Carbon-14 is mixed in the atmosphere with carbon-13 and carbon-12. All living organisms contain carbon, and although most of it is carbon-12, a trace amount is carbon-14. While the organism is alive, it is constantly exchanging carbon, so the ratio of carbon-14 to carbon-12 is constant. However, once the organism dies, the clock starts, and carbon-14 begins to decay, and the ratio between carbon-14 and carbon-12 decreases. Any organic matter preserved in an archive can be used for radiometric dating as long as the age is within about 200 to 40,000 years. So this might include pollen grains preserved in lake sediments or wood to confirm tree ring counts. There are many things in paleo archives that can be dated using radiocarbon dating. Try and think of some others. Try this activity to reinforce what we've learned about radiometric dating. Try the problems at the end of the activity to test your understanding of the material we've discussed today. There are 4 steps to being able to use a proxy to establish a climate variable. First, there is the calibration. We saw a good example of this in the thin ice video when they collected snow samples to measure proxies such as isotopes during periods when climate conditions are known. Calibration is used to determine the relationship between the proxy and the climate variable. Step 2 is verification. This is testing to see whether the calibration determined in one accurately estimates the climate variable of interest. Reconstruction or regression. Step 3. Now we apply our calibration to the proxy preserved in the archive to determine a record of past climate. Step 4. Validation. Now we check on our reconstruction using other archives or other proxies from the same archive. Let's look at what we can learn about past climates using proxies and these 4 steps. Let's start with tree rings. What characteristics of the tree rings can we use to determine climate? We can use tree ring width, wood density, vessel size, and isotopes. Today we will just consider tree ring width. How do we get to climate using tree ring widths? There are 2 key principles that underlie dendrochronology. The first is the principle of uniformitarianism. This principle assumes that the relationship between climate and tree growth that exists today existed in the past. The second is the idea of a limiting factor. A limiting factor refers to an environmental factor that is most important to restricting or encouraging the growth of the organism. Tree ring width is directly related to how well a tree grew in a given year, which is dependent on the limiting factor, which could include temperature, precipitation, snow cover, nutrients, even carbon dioxide. So how do we determine climate from tree rings? Let's review the main steps. First, we decide what climate variable we are interested in reconstructing. If it's temperature, we want to go to a site where tree growth is likely limited by temperature. Can you think of a good location? In alpine and northern areas, trees disappear above certain elevations and latitudes. In these ecotones, trees are likely limited by temperature. The photo here shows trees in a mountainous region. However, they're not limited by temperature. What do you think is limiting tree growth here? If you said moisture, you're right. The rocky soils hold little moisture, and this is in a particularly dry area. Once you've chosen a region that will provide trees that are sensitive to the climate variable that you are interested in, many samples need to be collected. Most often, samples are collected using a tree core, shown here, which removes a soda straw core of wood from the tree without causing harm to the tree. Back in the laboratory, tree rings are counted and measured. Cross-dating can be used to extend the record. This slide shows an example of cross-dating. Remind yourself what cross-dating is and how it works. Once all the tree rings have been counted and measured in all the many samples that we've collected, we can begin the 4 steps that we talked about earlier: calibration, verification, reconstruction, and validation. This plot shows the number of days in winter when precipitation occurred in northern Arizona and New Mexico. The red line shows actual observations, and the black inferred values from tree ring widths. Notice the section where the black line and red line overlap. Calibration involved using the first half of the record, shown in red, about 1980 to 1950, to determine a relationship between tree ring widths and number of precipitation days in winter. The calibration was then tested using the second half of the record where overlap occurs. This is from about 1925 to 1950. This allowed us to verify that the calibration worked. Then the calibration could be used to reconstruct the number of precipitation days back to 1700. Ideally, this record would then be validated by comparing it to some other proxy or another archive. This is another example of calibration and verification, this time for temperature shown in blue and tree ring width shown in pink. Part of this record would have been used to develop the calibration, and part of it would have been used to verify the calibration. The calibration on the previous slide, or one like it, was used to reconstruct temperature for the Northern Hemisphere going back to 1000 CE. Verification of the calibration can be determined by comparing the white line, the tree ring temperature reconstruction, to the red actual observations of temperature. This plot was developed by a team of scientists led by Michael Mann and is often referred to as the hockey stick. The plot clearly shows that temperature remains relatively constant from 1000 AD until approximately 1900, when temperatures increase rapidly. The hockey stick temperature reconstruction has been validated by comparisons with many other data, including temperature reconstruction from lake sediments, ice cores, and corals. This is an important record, showing clearly that Northern Hemisphere temperatures have become unusually warm. Let's see what we can find out from ice core archives.